Swayam Prabha. Digital India. Educated India.
Okay, so before we get into that, let me just quickly introduce dependencies, what are called true dependency, so anti-dependency and output dependency. Let me illustrate this by means of this example here. So here we have a sequence of instructions, right? And as you can see, the first instruction does a copy from R7 register to R3 register. The second instruction uses R3. The second instruction uses R3 as a source operand and does a memory load into R8 register. The third instruction also uses the R3 register and then adds 4 to it and writes it into the R3 register. You can see that there is a dependency, what is called a true dependency. The value produced by, the value produced by the first instruction, right, is actually what is being used by the second instruction over here. This dependency is what is called true dependency, or what is called read after write dependency. This dependency always has to be honored. There are also these other dependencies where this particular instruction is actually writing into R3, and this write has to happen only after this read has happened, because otherwise this instruction would not be able to complete it in a meaningful way, right? If you try to overwrite R3 register before this instruction has executed the load operation, or before this instruction has read the value of R3 for the load operation, then this instruction would not complete properly, and therefore this write must happen only after this read. So this write after read is essentially the anti-dependency, and that is what is being talked about here. Okay, the third type of dependency is output dependency, which happens because both the first instruction and the last instruction, they are using the same register R3, and the order in which they have to write has to be observed. For example, if you allow the third instruction to do the write first and then allow the first instruction to do the write, then obviously there would be a problem, because subsequent instructions which are over here, which are expected to use the value of R3 computed using this, right, may miss that and may just use the value of R7, which is wrong, right? So this dependency is what is called write after write dependency. We will focus more on the read after write dependency and how that would introduce stalls in our pipeline. Okay, so this is the ideal pipeline in which you have these 5 stages, right? And let's assume that the first instruction you are executing is an instruction which is adding R1 and R2 or putting the value into R3. If the second instruction actually uses, right, R3 as a source operand, then you can realize that the first instruction is going to produce the value of R1 plus R2 and write it into R3 only during the write back stage. But the second instruction is trying to read the value of R3 during the instruction decode phase, which is time step 3, whereas the value is going to be written into the written into the register only in the write back stage of first instruction, which is time step 5. So this kind of a problem, that is because of this true dependency between the ith instruction and the I plus 1th instruction, right? The value of R3 is being updated only in cycle 5, whereas you are trying to read it for the I plus 1th instruction in cycle 3, and this causes a problem, and therefore the pipeline has to be stalled, because if you want to read the value meaningfully, you have to wait until cycle 5. Or at least wait until cycle 4 is over, and during cycle 5, when the write is happening, you can read that. So both the I plus 1th instruction and the I plus 2nd instructions have to be stalled, and the I plus 1th instruction would start doing the instruction decode after cycle 5, when it can actually read this. This is what we call as the pipeline stall due to dependencies, right? The processor architecture would have hardware interlocks to detect these dependencies and stall them. So if you have a dependent instruction which is following the producer instruction immediately, then you are likely to have stalls. Whereas if these dependent instructions are farther, for example, if it is farther by 2 cycles in this example, then of course by that time that the dependent instruction comes to the instruction decode stage, the producer instructions would have written the value into R3 register, right? And that would have been an acceptable solution. So from a compiler writer's point of view, one solution that we can give for data hazards is that as far as possible, try to move these dependent instructions further from the producer instructions, right? And when you do that, you have to make sure that the dependencies are satisfied. So this is essentially what we call as instruction scheduling, reordering the instructions so that dependent instructions are far away from the producer instructions. But the reordering must be safe. That means that you should make sure that the semantics is still observed, right? That is, no dependence is violated. Okay, and you can actually do instruction scheduling either at compile time by the compiler, which is what we are going to discuss, or it can be done at runtime by the hardware, which we will not discuss here. That's for the computer architect to do, right? And this also happens when you have a load instruction and a dependent instruction, right? That's also another form of a dependency, and there also you may want to make sure that the dependent instructions are spread far apart. Here is a very simple example where I have a sequence of instructions, and as you can see here that there is a dependence from the first instruction to the second instruction, and also from the fourth instruction to the fifth instruction. In this particular example, I'm going to assume that the dependencies between a load and an immediately following add instructions or a dependent instruction would cause one stall cycle. So if I try to execute this sequence of instructions, assume that these two instructions, right, because of this dependency over here, would cause some number of stall cycles. The exact number of stall cycles does not really matter. It matters to the extent how many instructions you can pack in between, but other than that, it doesn't really matter. Okay, so let's assume here that there is a one stall cycle between a load and a dependent instruction, right? Now, as a compiler writer, during the instruction scheduling phase, you can reorder these instructions. You can reorder them while the dependencies in the instruction sequence is still satisfied. For example, let's say that we try to put a reordered instruction sequence in the following way. The first load instruction is maintained as it is, and because the second instruction is dependent on that, we want to put something in between, right? We move the other load instruction in between, and of course keep the rest of the things as it is. Then what happens is that the dependency from the first load instruction, right, R3 to the dependence instruction, right, is set apart by at least one instruction in between, and therefore it can actually remove that stall. And similarly for the second load instruction, the dependency is actually moved further apart, and therefore that stall cycle is also eliminated. So the compiler writer or the compiler can actually do this kind of an instruction scheduling to take care of data hazards or data stalls or stalls due to data hazards, right, by doing an instruction reordering. Okay, let's quickly look at control hazards and then see what happens there. Supposing, let's say, our ith instruction is a branch instruction, right? And you're going to find out that this is a branch instruction in the instruction decode phase. And during the execute phase, you are going to compute what is the target location and whether the branch should be taken or not. But before the instruction execution can go to the execute phase, in the next cycle, you have to fetch the next instruction. The question is whether the processor should fetch the i+1th instruction or the instruction from the target. We wouldn't even know what the target would be. We wouldn't even know that the ith instruction is a branch instruction until you complete the instruction decode phase. Therefore, when this instruction is being decoded and when the processor identifies that this is a branch instruction, it has to essentially stall, right, the next instruction, and it has to create bubbles in the processor pipeline. And when it creates this kind of a bubble in the processor pipeline, right, you incur wasted processor cycles, right? So you will kind of introduce a number of bubbles before you figure out whether instructions from the target location should be fetched or instructions from the following location should be fetched, and based on that, right, the instruction execution proceeds forward, right? So this is typically handled. So the number of stalls that are incurred can be reduced by doing some aggressive architectural techniques, as well as with the help of compiler to a certain extent, where what we have is the notion of what is called a delayed branching. In the case of a delayed branching, what happens is that the branch instruction and the subsequent instructions are always executed, right? So let me just explain this by means of what it is. So let's say you have a sequence of instruction. Then after the branch instruction, depending on the branch condition, you will either execute the instruction following this, or you will execute the instruction from out. This is the normal semantics. But in the case of a delayed branching, what happens is that you will always execute the instruction following the branch instruction, and the condition of control transfer takes place only after executing the instruction following the branch. The idea here is that that particular instruction can be used to avoid the delay slot that you were talking about, or to avoid the delay stall that we were talking about in terms of pipeline execution. So if I can put a meaningful instruction in this delay slot, and if the processor executes the branch instruction as well as the instruction following the delay slot can be one or more depending on how many cycles it takes to resolve the branch instruction. Then what happens is that, right, that stall cycle is not wasted. It's no longer a stall cycle. Some useful instructions are being executed. Again, there are techniques like where to move these instructions, and always you have to move an instruction which does not violate any dependencies and so on. For example, in this particular instruction sequence, right, the branch instruction is not dependent on the add instruction. Therefore, the compiler can do an instruction reordering and move the add instruction into the branch delay slot. First, execute the branch instruction and then execute the add instruction. And when it executes the add instruction, right, in the delay slot, it could actually save the stall due to conditional transfer or branches. Okay, so that's again what the compiler can do. Essentially, the idea here is that the compiler is trying to do some kind of an instruction reordering to avoid certain stalls due to control hazards. So we saw this instruction reordering for both, for saving stalls due to data hazards and control hazards. We will talk more about instruction scheduling when I come back and talk about machine dependent architectures. Right now, the idea is to say where these stalls are coming and why we need to avoid them. Okay, now let me skip the details of how exactly you will fill the slot, because that may not be very relevant here, and move on to the next set of topics. In fact, I want to cover instruction level parallelism very quickly, and also memory hierarchy to a certain extent. So maybe till about 11:40 we will continue. Okay. Now, so we saw simple pipelined processors and pipelined way of executing instructions, but you may want to, modern processors are capable of, issuing and executing multiple independent instructions and thereby exploiting instruction level parallelism. Your x86 processor in your laptop or in your mobile phone, right, already support instruction level parallelism, where independent instructions are issued and executed in a single cycle. This essentially helps you to improve the throughput, right? Again, you can actually achieve throughputs which are greater than, which is where you can actually execute multiple instructions every cycle, right? The question is, how do we identify these independent instructions, right? These independent instructions can either be identified by the compiler, and the compiler can pack these independent instructions, right, which happens in the case of VLIW processors, or the hardware can identify these independent instructions. Compiler can do some assistance in terms of doing some rearrangement, but essentially the hardware can do this identification of independent instructions and executing them in parallel, which is what happens in the case of a superscalar processor. Again, the role of the compiler is to make sure that this reordering, which is being done either by the hardware or by the compiler, right, is done in a way where all the dependencies are satisfied, but at the same time, the parallelism in the instruction level parallelism is exposed to the architecture. Okay, so let's see what that means in terms of the superscalar processor execution model. So typically we have a sequence of instructions. I have color coded them in terms of different colors. Let's say these instructions are fetched in program order, in the order in which they appear in the program, correct? And then when they are decoded, right, the processor understands the dependencies between these instructions, right? And then it figures out that the green instruction produces a value. Sorry, let me just look at, yeah, the green instruction produces a value which is going to be consumed by the gray instruction. Similarly, the red instruction produces a value which is going to be consumed by the gray instruction, and so on. And it also figures out that there is no dependency between the green instruction and the red instruction, or between the red instruction and the blue instruction. In other words, it figures out that the green, red, and blue instructions can be executed in parallel. Right? In the case of a superscalar architecture, this is determined by the hardware during execution. Right? And then what happens is that depending on the available functional units, right, whichever instructions which are not dependent on any operands, or which are independent, or which are data ready, are issued to those functional units, right, and they get executed. So for example, let's say in the first cycle, the green instruction and the blue instructions are executed. Then in the next cycle, the red instruction is executed, right? And as soon as the blue instruction completes its execution, the purple instruction can go for execution, and that goes in the next cycle. The gray instruction can only execute after the red and green instructions have completed and becomes data ready. So that happens in the next cycle. So all of this is done by the hardware. The hardware understands what is the relationship, or what is the dependencies between these instructions, and when can an instruction be issued for execution, and when it completes, what other instructions get ready, and so on and so forth. Right? That's essentially what is the superscalar execution model. Right? And after these instructions complete their execution, for certain reasons they commit in program order, and therefore that happens again in the original order, like what you see here, red, blue, I'm sorry, green, red, green, blue, red, and in the same order it happens over there. Okay, in terms of hardware, if you want to understand this very quickly, you have an instruction cache. Multiple instructions are fetched in a cycle and put in the instruction buffer, and from the instruction buffer, multiple instructions are taken, decoded, right, and then the dependencies between these instructions are understood. The instructions, right, I will skip the part relating to the reorder buffer, that may not be relevant for our discussion. The instructions are put in an instruction queue where the dependencies between these instructions are understood, and when those dependencies are satisfied, they are moved to the execution unit for execution. They perform the execution and write the result value in the register file through the reorder buffer, or they do load store with the memory architecture. This is what happens in the case of a superscalar architecture. It's not directly relevant to the compiler writer, except that if you can expose whatever instruction level parallelism or independences in instructions, it becomes easy for the architecture to exploit it. But a compiler writer does not have any direct role to play in the case of a superscalar architecture. Whereas in the case of the VLIW architecture, the compiler does the weightlifting, right? It identifies all the independent instructions, and it puts these independent instructions, or packs these independent instructions in terms of a single instruction word. The architecture or the hardware simply fetches, decodes, and executes this instruction, right? So here is an example for this. The compiler would identify these independent instructions and pack them as one long instruction word. That long instruction word is what is available from your program memory. You fetch it, and then that when you decode that instruction, you know what operations have to be performed and what are the operands. Those operations are performed and the result values are written. So this is what is called a VLIW instruction. And in the case of a VLIW architecture, the compiler has to identify these independent instructions and it has to pack them together as long instruction words. That again is a responsibility of the compiler, and the instruction scheduling phase of the compiler would actually work on that. We will come to talk more about this during the instruction scheduling discussion. Okay, now let me spend the next 10 minutes talking about memory hierarchy, which is also very important for our understanding. Right, all of you know about memory hierarchy. You know that, right, the memory hierarchy consists of the main memory, the multiple levels of caches and registers and so on. The importance of memory is that memory, it takes several cycles to access the memory, right? Whereas instruction execution happens, pipelined instruction execution, when we are talking about executing one instruction every cycle. But you have to fetch the instruction from the memory. You have to possibly fetch or store, operands for load store instructions from the memory. And if they take several cycles, then that becomes extremely slow. So what you try to do is that in processor architectures, you have the several levels of memory hierarchy, which essentially exploits the principle of locality to make sure that the effective memory access time is reduced to one cycle or a few cycles. Okay, let me skip the details here and then go directly here. So as you know, the memory hierarchy consists of the main memory, then multiple levels of caches, and then of course registers. And as you go down the memory hierarchy, right, the size of the hierarchy increases. For example, you have few tens of registers, maybe few tens of kilobytes of L1 cache, maybe hundreds of kilobytes of L2 cache, and maybe a few megabytes of L3 cache. Then of course you have memory, which could be in the order of maybe a few tens of gigabytes to maybe even hundreds of gigabytes. And of course underneath that you have the secondary memory, which is the disk, which is in the order of maybe hundreds of gigabytes to terabytes. But if you look at the access time in the memory hierarchy, the access time goes the other way, right? It's possible to access your processor registers in less than a cycle. If you are wanting to access your caches, it takes from a couple of cycles for L1 cache, maybe to 5 cycles for L2 cache, and maybe to few tens of cycles for L3 cache. But to access the main memory, it takes several hundreds of cycles. And if you want to access the secondary storage, then it takes several tens of milliseconds, which could be in the order of 10⁶ processor clock cycles, right? So that's really the memory hierarchy. And the reason the memory hierarchy works is because of the principle of locality. The principle of locality essentially is divided into temporal locality and spatial locality. In temporal locality, we talk about the same data item being accessed again and again in time. That is temporal locality. And therefore, if it is brought into, right, in the memory hierarchy at higher levels like the L1 cache or the L2 cache, then they can be accessed much faster. Spatial locality talks about the locality which is offered by accessing adjacent elements. Whenever these elements are brought from memory to cache, they are brought as a group of words, right? A group of words called a cache block is what is being brought from your memory to L1 cache or memory to L2 cache and then to L1 cache. Therefore, these adjacent words which are also brought essentially bring in what is called spatial locality. Right? Typically, you will have multiple levels of caches, L1 cache, L2 cache, and so on. If the data item is available in L1 cache, it can be accessed in 1 or 2 cycles. If not, you first search in the L1 cache. If it is not there, then you go to the L2 cache from where it is accessed. Maybe it takes a few tens of cycles. And then if it is not there, it has to go to the main memory. Right? Typically, we talk about locality. And the locality is available both in instruction access as well as data access. As I mentioned, you also talk about L3 caches. So one thing that we talk about in terms of memory and memory hierarchy is that how does the memory hierarchy reduce the average memory access time? The average memory access time is essentially calculated if most of the time you're going to get the data from your L1 cache, right? Then the access time is essentially determined by L1 cache's access time. So for example, if I say 90% of the time I'm going to get the data from L1 cache, and L1 cache has only one cycle access time, then one cycle access time initially, and then for the remaining 10% of the data which is not there in L1 cache, I have to get it from L2 cache, right? So whatever is the access time from the L2 cache. And let's say if in that 10%, 5% is available in L2 cache, then that 5% is going to get access time from L2 cache. The remaining 5% has to come from memory, and that is the access time of the memory. So in this particular example, we will say the time taken is equal to one cycle for L1 cache access time plus 0.05 multiplied by L2 cache access time plus 0.05 multiplied by memory access time. So that's essentially how you calculate the average memory access time. This formula is a simple formula assuming only one level of memory hierarchy, only L1 level. But if you have multiple levels, I have already told you how to calculate the average memory access time. Okay, let's try to quickly understand how caches are organized, and we are going to talk about it in the context of the set associative cache organization. So the memory is divided into blocks, which is basically consecutive words. Typically, you talk about a block of 32 bytes or 64 bytes, right? And the caches are divided into blocks and sets. The block is same as the size of whatever the block that we talked about in the context of memory. So it is able to hold this 32 bytes or 64 bytes. And then the cache itself is divided into a number of blocks, and each block, not each block, a set of blocks is essentially what is called a set. So let me just give you the diagram here so that you will understand. So for example here, right, each block consists of 4 elements or 4 words, let us say, right, that is 32 bytes. And the memory is divided into a number of blocks. Similarly, the cache is also divided into a number of blocks. Further, the cache is divided into a number of sets, each set consisting of multiple blocks, right? And now in the case of a set associative organization, right, each one of the memory blocks can go to a fixed set, but within that set, if there are multiple blocks, it can go to any one of the blocks. That's what is called the set associative organization. The direct mapped organization, you will have only one block per set. Therefore, it can go specifically to that particular set and that particular block. It's more fixed mapping. Whereas in the case of a set associativity, there is a little bit of flexibility because among the blocks within a set, it can go to any one of the blocks. In the case of a fully associative cache, there is only one set and all the blocks are in that same set. Therefore, any memory block can go to any cache block. So you can actually think of set associative organization as the most generic cache organization, and then think of direct mapped cache as a restricted way in which each set has exactly one block, or a fully associative cache organization where you have only one set and all the blocks are in that particular set. Okay, so what happens is that the memory blocks are brought into the cache, and when they are brought into the cache, they are actually brought in as the consecutive words. So for example, here, if you assume that there are 32 bytes in a block, then all of these 32 bytes are brought in together. Okay, and it can go to, depending on the mapping here, for example, blocks 0, 4, 8, etc. would get mapped to set 0. Block 1, 5, 9, etc. would get mapped to set 1, and so on. Right? All right. So why are we talking about all of these things? Now, again, from the compiler perspective, we need to understand when a program is accessing the data items, is the accesses kind of contribute to data locality or not, right? We could actually write some programs in which the data locality is completely ruined and the processor essentially gives you, the caches do not give any benefit at all. Let's try to understand that with the help of one example over here, right? Before we do that, we will simply say how exactly are the memory blocks identified, whether they are in the cache or not, Many of you would have gone through this exercise in your undergraduate course in computer organization. I will not go into the details, but essentially point out the fact that the address is divided into three parts. What is called the offset part, which is essentially used for accessing the data item within a block. The index part, which is used for accessing which set or which block is, if it is a direct map to cache, which block is going to have the data item. And the tag essentially tells you whether that particular and the block that we are talking about contains the memory block that we are interested in, right? So it is essentially divided into these three components. Okay, now what are we doing in terms of time? Okay, right. Now let me do one thing instead of rushing this. Let me stop here and maybe spend 5 minutes or 10 minutes in the next class that I'm going to deal with, and then talk about it. I will post these slides for everybody to access, and you can actually go through the example and see if you can understand it, right? Maybe that's a good idea. Instead of rushing this in 2 minutes, what I will do is I will post the slides in the website that the volunteers have provided. You can access them and you can have a look at it. And hopefully when I come back on Thursday, I'll try to complete the rest of the discussion, and then from there we will take it forward. Okay,